In the past, my input and output for functions have been x and y. And x and y have been visually represented as lines going horizontally and vertically. Trigonometric functions are a little bit different because its input and output values are different. Its input value is an angle, and its output value is a ratio. So the structure of the domain and range is going to be slightly different than some polynomial function. So let me get into that. And the easiest way to kind of be able to visually see this is by using the unit circle, which is a circle with a radius of 1. I have here written out all of the trigonometric functions. Actually, I need to explain this real quick. This is a sector of a circle S, measured in radians. And this line T is equal to S. It would be as if I had stretched S out into a straight line. So what T is just S stretched out. So I can do all of my trigonometric functions. If S is in radians, it's an angle, so I can think of it as just sine of theta instead of T, where T is in radians. Cosine of theta, b over r, a over r, b over a. R is the radius of the circle, which in this example is 1, so it would just be b and a for sine and cosine. But if I had a point somewhere else, I could expand a circle large enough to encompass that point, and the radius would be different. I would have to divide out by the radius. But that's not really the point. The point here is to talk about the domain and range of trigonometric functions. So as I said before, S is a sector of a circle, and T is that sector of the circle but stretched out. And what I'm going to do is take T as my domain, because if I'm going to take T as a distance along this circle, so I can go T, let's just say 1 unit, and say it was right here. That's going to correspond to a particular point. I can go a little bit further and go to point AB. That's going to correspond to a particular point. I can go greater T all the way over here. That'll correspond to a point. I can go backwards. I can go T minus 5, whatever the units are. It might be somewhere over here. That's going to correspond to a particular point. Each T value is going to correspond to a unique point, and that is the essence of a function. Each x value has only one y value. If an x has more than one y value, it is not a function. So T being able to go around the circle, and each location having a unique point, there are no points that are going to be the same for T. And it might look like I would run out of places to go because I could only go around one time. However, that's not true. T is sort of like the x-axis. I can think of T as a horizontal axis. And it goes infinitely in the positive and negative direction, because I can go around more than once. I can go, well, the circumference of any circle is 2 pi times a radius, but for here, since it has a radius of 1, it's just going to be 2 pi. So if I go around 2 pi times, if I was thinking of sine, b over r, it would be 0. So I would have 0. But if I went around again, so if my angle was 4 pi, and I went around once, 2 pi, and I went around again, 2 pi, then my points for sine theta would be for 2 pi, 0, and for 4 pi, 0. And these are unique points. because the x's are not the same. It's as if I had a horizontal line in a coordinate plane. The x's all have the same y, but they are still unique points. So this is a function. The only thing that is different is that the range is not a line like in the previous types of functions I've been dealing with. Because the only available numbers to satisfy these trigonomic functions are going to lie along this circle somewhere. So the range can only be these points on the circle. So while the domain is not limited in the trigonomic functions, the range is. So for let me say for polynomials, whatever, the domain, actually I'll do it like this. Polynomials trig. Domain is a horizontal line, x-axis, then it goes to minus infinity and positive infinity. Trigonometry, trigonometric functions, has some axis t, and it goes to negative and positive infinity. The range is the y-axis in polynomial functions, and it goes to positive and minus infinity. In trigonomic functions, it is a circle with radius r, and all of the range is located on the edge of this circle somewhere. So that is the structure of trigonomic functions. It's very interesting to see how triangles and circles are connected. It's not, I guess, intuitive in the beginning. It doesn't really seem that there would be a connection between them, but there's a very strong connection between triangles and circles, and this is it. When I'm going around this circle for different functions, say I'm using sine, I start out at 0, I have the opposite side, which at horizontally it would have no opposite side, and the opposite side would be 0. And then as I go along the circle, the opposite side of the triangle that would be along here would be increasing until I get all the way to 1, where the opposite side would be equal to the hypotenuse, and then it's just 1. And then it comes over here and it starts decreasing again, then goes to 0, starts increasing again, goes to 1, starts decreasing again, goes to 0. So it's a periodic type of function. The only thing that's different is here sine is positive, here sine is positive as well, here it's negative, here it's negative. And the only difference really is the sign of the trigonomic function depends. Here all of them are positive. Here sine is positive because sine would be the opposite side or the y. Here tangent is positive because both x and y are negative. B over a, negative divided by negative, makes it positive. And here cosine is positive because the x number is positive and the y value is negative, and the adjacent side is the a side, which is the x, so therefore it's positive.